Alright, time to move on to Faraday's law, which is really good. Faraday's law is one of, well, it's called Faraday's. Faraday was the guy that did all the electrical sort of experimentation in the mid-1800s and probably 1830s, 1840s. By about, I think, 1860, someone called Maxwell had worked out these four equations that pretty much summed up everything that electricity and magnetism could do, and they're called Maxwell's equations. Faraday was still alive, so this was great. To give you an idea of what this means to physics people, Einstein only had two pictures of two people on his wall, and one was Faraday and one was Maxwell. This is what he wanted for all the laws of physics to be encapsulated in some reasonably simple equations, and he went ahead and did it for gravity in what's called the general theory of relativity, and he found that it was, hugely more complicated than what Maxwell had done, and he wasn't really the best mathematician there ever was, so found it very difficult. Anyway, one of the main equations is called Maxwell's equation, and we'll get, or Faraday's law actually, and we'll get to that. First, we just got to talk about flux. When you have a area with a magnetic field going through it, all right, then the magnetic field strength times the area is called the flux. So we can say flux, and this is our symbol for it, is equal to magnetic field strength times an area. So it's not magnetic field by itself. It's not area by itself. It's magnetic field strength times the area. Flux is measured in Webers. We know that magnetic field strength was measured in Teslas after the great electrical engineer Nikola Tesla. Weber's, the symbol is WB. All right, so that's flux. So Weber is equal to Tesla square meters. All right, or you could say the magnetic field is equal to Weber's per square meter. Right. Now you've had a little look at flux. We can now look at Faraday's law. Faraday's law, there's a couple of different ways of doing this. When you get to Maxwell's laws properly at university, you're going to do what's called vector equations. And we really haven't done vectors much in physics, but Faraday's law looks like this. It says, I'm just thinking which way I'll do it. I'll use that symbol. E, that's our magnetic potential, is equal to the negative of the change in flux over change in time. Normally I prefer to do it like this, differential. But you're going to see it as delta. So delta, by now you've done a little bit on gradients and started your calculus and all that sort of thing. So you'll know that the delta gives you an approximation to the gradient. And as the delta t approaches 0, we end up with a specific gradient at a point on a function, and that's what we've got with a d flux dt. Now the thing is, what is this saying? It's saying that the voltage is equal to the rate of change of the flux with time. So no change in flux, no voltage. All right, so no change in flux implies no voltage. So if the flux is not changing, there is no voltage. Let's give you an example of that. If we've got a really big magnetic field, like this, we've got a little loop of wire, which has obviously got an area, and it's moving through that field. So although it's moving through that field, if this field is uniform, that means consistent throughout. If it's moving through that field, it's changing position, but its area is staying the same and the magnetic field strength is staying the same. So that means the flux is not changing. Delta flux over delta t is equal to 0. It's not saying there's no flux there. It's saying the change in flux is 0. And that would give us, that would mean that V equals 0. So that's the way we actually look at Faraday's law. So once you know how quickly the flux is changing, you can work out the voltage. So when we've got a loop, let's have a look here. Got our big loop and it's rotating in a magnetic field, right? Because we've made that a north and we've made that a south. So this loop, and I think I'll put them in across there, come across there, down like that. Oh no, it's a crappy loop. There you go. It should have been down like that, shouldn't it? Okay, let's ignore that bit there. So we're rotating this. At this stage in the vertical position, the magnetic field is running from north to south. So actually those X's would only be X's if we look from this side, right? And from this side they'd be dots. Get rid of those. But anyway, you all know that the magnetic field's going north to south through that loop. So we definitely have a flux going into that loop. We've got a flux and we've got an area. The area would just be, we'd have to just multiply this distance here. If we call that L, if we call that, I don't know, A, L times, I shouldn't call it A, should we? Let's call it L times 2R would give us the area, right? So that would be the area times the magnetic field strength. That would be the flux in this position. But the flux is changing. So when this loop rotates into a horizontal position, the flux is 0. So vertical is maximum flux, whereas horizontal equals 0 flux. Hopefully you can see that. So the questions you sort of get in year 13 are questions where they go, okay, in a 90-degree turn, it's gone from maximum flux to 0 flux. The flux has changed from the B times the A, divided all by the time it took, and they're going to give you a voltage. This is an average voltage. All right? If you really wanted to know the specific voltage, you would have to do the D flux, dt. It's a negative voltage. Where's the negative come from? All right. Now the negative comes from the fact that the voltage produced is in the direction to oppose the change in flux. Remember, this is Lenz's law. This is Lenz's law. So when a flux changes, okay, it's asking, and again, this goes back to that whole one where we were pushing a magnet into a solenoid or pulling it out. Remember that one where we had a solenoid and we pushed in a north and it produced a north when we pulled it out. So pushing it in produces that. But when we pull the north out, it produced a south on that end. Remember that? And we said that was Lenz's law. It's opposing the change in flux. So if the flux is getting bigger, all right, it's going to have a field that goes against it. What does that mean? That sort of means like if we had a field like this, and if we had a loop in that field, and these X's are getting bigger, they're getting bigger, this field is increasing. We don't have to know why it's increasing, but they're getting bigger. Then this loop is noticing a change in flux. The area is not changing, but the magnetic field is. So if the area is staying the same, but the magnetic field's increasing, then that is changing. It's getting bigger. Now, those are X's going into the loop. Now, how can it decrease that field? Well, if it could produce a field coming out of that loop, then it's going to counteract the change of the X's getting bigger. So you use your right-hand rule to figure out which way a current flows around this red wire to oppose the change. Right? So if I want to oppose the X's getting bigger going through, then I need to produce a field coming out. And I can do that with my right hand wrapped around the wire and a current flowing this way. So to oppose the X's getting bigger, I need a current to flow that way. Because that, if you use your right hand grip rule for a magnetic field, level 1, your fingers curl around the wire, coming out through the inside, and that opposes the field going in. So that gives you that direction. But the interesting thing is, if the X's had been getting smaller, still X's, but they're getting smaller, same loop, then if they're getting smaller, so this one was X's getting bigger, if they're getting smaller, it doesn't like that either, and so it's going to try and support the field. And so to support the field, it's going to produce a current that makes the magnetic field lines go inside the loop to support the x's that are getting smaller. And to do that, it needs to make the current go this way. So this is Lorentz force law. And, no, sorry, this is Lenz's law, right? Lenz's law. But I'm going to show you how this all comes down to Lorentz force law anyway. But this is Lenz's law, which you need to know. And this is all to do with Faraday's law, which we've covered.